In this video, I'll consider one numerical on node analysis. Find node voltages V1, V2 and V3. This is the given circuit. We need to find node voltage V1, V2 and V3. I will use node analysis to simplify this. So this is the given circuit. So as we know, in node analysis, we need to apply KCL to individual nodes. For that, first let me mark all branch currents. Here in this branch, there is a 4 amp current source. Let me assume current I1 is flowing in this branch. Let this is current I2. Let this is current I3 and let this is current I4. So here we can observe that in between node V2 and V3 there is a 5 volt voltage source connected. It means V2 and V3 are super nodes as voltage source is directly connected between these two nodes. So we can say V2 and V3 as super nodes. Let this be plus and this is minus. That is here V2 and V3, that is node V2 and V3 are super nodes. So as we know, in super nodes the algebraic sum of currents is 0. That is at super nodes I can say algebraic sum of currents are 0. So here at node V2, let me see the currents. That is at node V2 we have I1 and I3 currents. So here at node V2 current I1 is incoming, current I3 is leaving. Let me consider incoming current as positive, outgoing current as negative. So here I1 is incoming current, I will call it as positive, and I3 is leaving, that is I can write it as I3. So at node V2 there are two currents, one is I1, one is I3. Similarly at node V3, that is at node V3, so here one I2 current is incoming and I4 is leaving. So I can say plus I2 and I4 is leaving, I can take it as minus I4. So according to the definition here we can see that at super nodes algebraic sum of currents are 0. So sum of these all is equal to 0. That is I1 minus I3 plus I2 and minus I4 is equal to 0. Let me represent all these currents in terms of node voltages. So here we can observe that I1 is nothing but V1 minus V2 divided by 0.33. That is V1 minus V2 divided by 0.33 minus I3. So I3 is nothing but V2 divided by 0.2. That is V2 divided by 0.2 plus I2. So here I2 is the current which is flowing from V1 towards V3. So we should write it as V1 minus V3 divided by 0.5. That is V1 minus V3 divided by 0.5. And here we can observe that I4 is nothing but V3 divided by 1. That is V3 by 1 is equal to 0. Let me simplify this. I can simplify it as V1 by 0.333 minus V2 by 0.333 minus V2 by 0.2 plus V1 by 0.5 minus V3 by 0.5 minus V3 is equal to 0. Or I can write V1 in bracket, here we have 1 divided by 0.333 plus here we have 1 divided by 0.5 plus, so here there are two V2 terms, so let me take it as minus V2. So here we have 1 by 0.333 plus 1 by 0.2 and minus V3, we have 1 divided by 0.5 plus 1 is equal to 0. 0.333 means 1 upon 3, that is nothing but 3. Here 0.5 means 1 upon 0.5 means 2. So 3 plus 2 is 5. So here we have 5v1 minus, this is also 5, that is 5v2 minus, here we have, so 1 upon 0.5 means 2, 2 plus 1 is 3. That is 3v3 is equal to 0. Let me call it as equation 1. Here we can observe that as V2 and V3 are supernodes, I can write plus n is connected to V3 minus n is connected to V2. We should write it as V3 minus V2 is equal to 5 volts. That is 5 volts. Let me call it as equation 2. Let me write only number. So now V2 and V3 are done. Now we have to apply KCL to node V1 because node V1 is independent node. We must apply KCL to node V1. That is apply Kirchhoff's current law to node V1. That is here 4 amp is incoming, I1 and I2 are leaving. I can write 4 is equal to I1 plus I2, that is 4 is equal to I1 is nothing but V1 minus V2 divided by 0.33, V1 minus V2 divided by 0.33 plus I2 is nothing but V1 minus V3 divided by 0.5. V1 minus V3 divided by 0.5, or I can write 4 is equal to 1 upon 0.33 means it is 3 V1 minus V2 plus 1 upon 0.5 means 2, that is V1 minus V3, or I can write 4 is equal to 3V1 minus 3V2 plus 2V1 minus 2V3, or I can write 4 is equal to 5V1 minus 3V2 plus, that is minus 2V3. Let me call it as equation number 3. So now we are supposed to solve equation 1, 2 and 3. That is solving equation 1, 2 and 3. So to use the calculator, first go to the mode. In mode, select equation mode, that is 5. Click on 5. It will choose, it will get this window. Here we can see that there are different options. One is with respect to two variables, two unknown variables. Here we can see that 3 equations and we have 3 unknowns, V1, V2, V3, 3 unknowns. So we should choose the option 2, where here we have 3 unknowns x, y, z. Here it is x, y, z. Here the unknowns are V1, V2 and V3. On right hand side Dn means these values. Now let me choose option 2. Just click on 2. It will, you will get the matrix like this. So just feed the values. So first A is nothing but coefficient of V1, that is 5. Just press on equal. Then it is minus 5, press on equal. Then it is minus 3, press on equal. Then D is nothing but this value, that is 0. Now automatically it will go to the second row. In second row there is no V1, it means V1 is 0, equal sign. Then coefficient of V2 is minus 1, that is minus 1, equal to, then coefficient of V3 is plus 1, that is 1. Then here we have 5, just click on 5. Then in third equation, coefficient of V1 is 5, that is 5. We have minus 3. Then we have minus 2, that is minus 2. Then it is 4. This side is 4, so take it as 4. Then click on equal once again. It will show the values. Now it is showing x. X is nothing but first unknown, that is V1. There 7. V1 is equal to 2.4667. Just press on equal once again. So V2 is minus 1 by 3. So we have V2 is minus 1 by 3 means 0.33 volts. V3 is 4.667. So V3 is 4.667 volts. So these are the node voltages V1, V2 and V3 for the given problem. Thank you for watching.